Now let's figure out how to combine resistances. Like if you have two resistance, one after the other, as earlier told to you in series, then how to suggest a value equivalent to the two resistance, a value of a resistance which is equivalent to the two resistance, and replace it with the two resistances in the circuit, simplifying my circuit. Similarly, if we have two resistances in parallel, then what can be the equivalent value of these two resistances? One resistance having an equivalent of these two, so that we can replace the circuit with one resistance instead of two or more. So this is parallel combination, that is series combination, and that's our aim to do. Now intuitively, can you tell me if this resistance was say 1 ohm and this was 2 ohms? What would this resistance be? More than 2, less than 2, less than 1, something between 1 and 2? What do you feel? Yeah, maybe more than 2. There's a resistance in the path and then the other resistance in the path. So it seems as if you have a resistance greater than any of the two. So a fair guess would be more than 2 ohms. Maybe 3 ohms, maybe something else. Maybe it's a simple addition of 1 plus 2 gives you 3 ohms. Maybe it is 1 square plus 2 square under root gives you root 5 ohms, which is again greater than 2. So we'll check out. And again, what do you think? If this was 1 ohm and this was 2 ohms, both of them combined will give you a resistance of how much? Will it be greater than 2? Something between 2 and 1? Or something less than 1? So seems like something between 2 and 1, right? We'll see soon. Now let's take the analogy of a water circuit again to understand these situations more closely, particularly the series one first. So the circuit over here shows a pump and a path for the water to flow. So the pump is pumping water in this direction. There is a clog over here which is resisting the water flow, and then water is coming out and getting back into the pump. That is same as you would have a battery trying to push current through a resistance. Now suppose I say that the water which was flowing was say 10 liters per second. 10 liters per second would be too much. Let me put it as 10 liters per minute. 10 liters per minute. Now if I ask you that with the same pump and the same initial clog having X resistive value, if I put another clog of say Y resistive value, maybe more, maybe less in the path, then what do you think? The water which is flowing would remain as 10 liters per minute, or will it reduce, or will it increase? Now we can easily predict that the water flow will be less. Let us look at the situation more closely. Which part will have the water flow less? Will this initial path flow be the same and then it will reduce over here and then reduce further over here, or something else is happening? Take a pause and think. You need to follow the basic rules. Whatever is coming out of the battery or the pump is going into the pump. Pump doesn't have its own water to push through. It will receive and it can push the same water through. So the thing is clear. Whatever is coming in, say A liters per minute is going out, is equal to whatever is coming in, which is A liters per minute again. Whatever is coming in, the same amount is going out. So what happens when you put a clog over here? It's not that 10 liters per minute will flow till this point and then reduce through the clog and become lesser, say 8 liters per minute. No, it is not going to happen, because, and let me complete it further. And further, this clog, using the same logic, reduces it to say 6 or 5 liters per minute. And this is not going to happen. Why is it not going to happen? Because it defies the fundamental rule that whatever is coming out has to go back in. In this case, only 5 is coming in and 10 is going out. So where will that 10 come from? It can't. So pump is going to run dry. So what happens is, wherever you add the clog, no matter where you add the clog, the flow is affected right on the onset. The flow over here itself will become, say, 5 liters per minute, and then whatever was flowing, the same amount is going to go through here, and then this part, and it is going to go through there. If you're going to add some resistance in the flow, some clog over here, it's not that it is going to make the flow less after this. It is going to affect the whole circuit. Let me give you an example over here. Say this is the overhead tank of your house, and the pipeline runs down to your bathroom, and there's your tap. When you open the tap, the water is going to flow in the pipe. The pipe will be full of water and is going to come out. Now when you close the tap, when there is no flow over here, when you close the tap over here, what is going to happen? Is it that water is still going to flow till the tap and then not go forward? No, that's not going to happen. The water is going to stop right at the source. Right at the source, there is going to be no flow when you're closing over here. Same way, if you open your tap halfway through and you make the flow less, say it's leaking, few drops are going down, then how much is the flow in the pipeline? It's the same. Whatever drops, whatever amount of milliliters coming out per minute will be the milliliters coming out of this tank per minute. This flow, X liters per minute, is going to match this flow, X liters per minute. So it is not where the clog is, it is going to affect the whole circuit, the whole line. That's the point. Now the other point is, since adding a clog has affected the whole line and the current or the water flow has decreased, means these two clog is equivalent to a big clog. These two clog is equivalent to a bigger resistance. So the value was X and Y. So the equivalent clog will be having a value more than X or more than Y. Now let's analyze the parallel circuit. Now the parallel situation is not as simple, so I'm going to give you two situations. Say one is, people are going to go to a movie hall. There's the screen, there's a movie going on, and there's a lot of rush. Lot of people are in queue. Lot of people are in queue, one after the other, one after the other, one after the other. And there is frisking going on before you can enter. They are checking whether you're carrying bomb or not. So this is one pathway, and that's the other door. These two doors are there. Now one unfortunately is closed for now. No path over here. One is closed. So there's only one security guy who is allowing people to go through. Some unfortunate ones tried out this path just to find that it was closed, and now they are stagnant, just standing over there. Can't go back. People over here are not allowing them to go back. They're just waiting for the door to open. Don't worry, I'll open the door in a while. With water circuit, a similar situation would be there are two paths, one having certain resistance and the other one having infinite resistance, totally blocked. So useless even mentioning that path. And then there is a pump, which is a battery pumping the water, through the resistance. That's the cinema hole over here. So let me do this situation first. Say this security guy over here, the security guy over here allows 10 people to pass through per minute. So how many people will be coming out over here? What do you think? How many would be coming out over here? Yes, that would be 10 people per minute. How many would be here? How many would be going over here? So since the security guys are like 10 people per minute, the movement over here at any given point over here would be 10 persons per minute. And what do you think? How many would be moving over here and here? Nobody over here is being allowed through the gate. So the movement over here is 0 persons per minute. And the person who are moving here in this line is because of this gate alone, and it would be 10 people per minute. A similar situation over here is this clog is allowing 10 liters of water to flow through per minute. Then the water flowing here would be 10 liters per minute, the water flowing here would be 10 liters per minute, and the water flowing here would be 10 liters per minute. The pump is pumping out 10 liters per minute and it is receiving 10 liters per minute. Now if I say the pump pumps out more than 10 liters per minute, that means the resistance of the circuit has become less. If the pump pumps out less than 10 liters per minute, then the resistance of the circuit has become more, which was the situation earlier. When I put a clog over here in the path of the current going, then the pump was pumping less than 10 liters per minute. Now let me open up this gate. If this gate opens and a very slow security guy is allowing people to pass through, but he is at least allowing some to pass through, say 1 person per minute, then can you tell me the flow in each path? Say what is over here? That would be 1 person per minute. What will be the flow over here? 10 are going through this. Will that reduce? No, that won't reduce. There are so many lined up and they're just waiting. The people can go at any rate. They can go at 20, 30, 40 per minute if they are allowed. But this guy and this guy are stopping them. So would this reduce? No, this won't reduce. This will remain 10 people per minute. It will keep on passing 10 people per minute, 10 persons per minute, and this gate would pass 1 person per minute, and the total over here would become 11 persons per minute, 10 from that side and 1 from this side. So that will become 11 persons per minute. How many persons would be passing at this point? At this point, the number of persons passing would be 11. 10 going this way and 1 going that way. So what are we seeing? We are seeing that the rush has increased. We have added a path which was in parallel to the original path. This added path is having a very high resistance, but because it is allowing very less movement, but still it is increasing the net movement. The net movement has increased. I'll repeat this point. I've added a path which was a very high resistive path. It was allowing very less movement in the path. Nevertheless, it has increased the overall movement. Similarly, let me add a path over here which is highly resistive. Lot of clog in this path, but still some water can leak through. And how much is going through? Say 1 liter per minute is going through. So the same thing has happened over here. The overall flow has become 10 plus 1, which is equal to 11, and what is going back to the pump is again 10 plus 1 over here, 10 plus 1, which is equal to 11 liters per minute. So what are we seeing? Adding a resistance in parallel is in fact decreasing the overall resistance. Why it has decreased the overall resistance? Because the overall flow has increased. The overall flow has become from 10 to 11 liters per minute. So the pump feels less burden in pushing them through. So the resistance of the path has in fact decreased. So no matter how much resistive a parallel path is, it is going to ultimately decrease the overall resistance of the circuit. answer the initial question where I had asked you if two resistances are there, 1 ohm and 2 ohm in parallel, what do you think their net combined resistance would be? Greater than 2, between 1 and 2, or less than 2? It would be surprisingly less than 1. That's equal to 2 by 3, by the way, which we'll be learning shortly. So again, summarizing the 2 points. One, when we add resistance in series, the net current decreases. That means the effective resistance has increased. The resistance was, say, R1, R2, R3. The net resistance would be more than any one of these, more than the highest of this. Fortunately, we get a very simple formula. It comes as R1 plus R2 plus R3. But we'll not take this as granted, we'll prove this. And when we add resistances in parallel, like this, no matter how much resistive the path is, we are adding a parallel path. We are adding a parallel path. Adding all these resistance would in fact going to reduce that overall resistance of the circuit. Say this was 1 ohm and we have added 100 ohms, 200 ohms, 1000 ohm, whatever, 2 ohms. The net resistance is going to be less than had those been not there. It is going to be less than even 1. The reason is that whatever current, say 5 amps, was flowing earlier, that current will remain, and on adding of extra paths, more current is going to go through, a very less one, 0.0001 maybe. But still, the net current is going to increase, and the net current is going to be that 5 amps plus whatever current is in the other path, 0.001 or whatever. So the battery is able to push more current through the circuit. So it thinks that the total resistance of the circuit has reduced. So that is what has happened. So the effective resistance of resistances in parallel would be less than the least resistance in the parallel lot. And effective resistance in resistances in series would be more than the most in the lot. We are going to derive the formula and get the exact values. I hope you have understood why the equivalent resistance of resistances in parallel would be less than the least in any of the parallel branch.